Assignment problem. Question is, which of the following method is commonly used to solve assignment problem? Given four options: stepping stone method, Hungarian method, northwest corner method, and Vogel's approximation method. Mainly, there are four methods to solve assignment problem: Hungarian method, enumeration method, simplex method, and transportation method. The most common method to solve assignment problem is Hungarian method. As you see, the mentioned methods, stepping stone methods, and northwest corner method belongs to transportation problem. Vogel approximation methods belongs to also transportation methods. Stepping stone methods, it can be used in the process of improvement of transportation problem. So the correct answer is Hungarian method. Also, we have to mention that the Hungarian method is the most used, commonly the most used to solve assignment problem. Assignment problem A. Solution to the balanced assignment problem is binary due to linear formulation, non-empty visible, approximation algorithm, unimodularity probability. Okay. The correct answer number 4, grade 1. But here I would like to explain why option 4 is the correct answer. An assignment problem is a special case of the transportation problems, where the matrix must be a square matrix, and in every column only one situation is possible. The square matrix has the same number of rows and columns are equal. For an assignment problem, the number of variables equal n power 2 and the number of equations equal 2n minus 1, where n is the number of rows and columns. The assignment matrix only contains either 0 or 1 in the respective row or column. The balanced assignment problem are those type of assignment problem where the number of facilities is equal to the number of jobs. The solution to the balanced assignment problem is binary due to unique modularity algorithm. So the perfect solution for the mentioned question is number 4 in modularity probability. An assignment problem of size 6 times 6, the total number of decision variables in the objective function is 12, 11, 6 or 36. An assignment problem of size n times n or nn, number of decision variables is n power 2, and if n equals 6, then the decision variables equal 6 power 2 equal 36. Basic assumptions of game. Each player has available to him a finite number of possible strategies. The list may not be same for each player. Player A attempts to maximize gains and player B to minimize losses. The decisions of both players are made individually prior to the play with no communication between them. The decisions are made simultaneously and also announced simultaneously so that neither player has an advantage resulting from direct knowledge of the other player's decisions. Both the players know not only possible payoffs to themselves but also others. So these are 5 basic assumptions of game. Each player has finite number of possible strategy. Player A attempts to maximize gains while player B to minimize losses. The decisions of both players are made individually prior to the play. The decisions are made simultaneously. Both the players know not only possible payoffs to themselves but also to others. The Big M method is another method of removing artificial variables from the basis. In this method, we assign coefficients to artificial variables and desirable from the objective function. If objective function z is to be minimized, then a very large positive price, for example called penalty, is assigned to each artificial variables. Similarly, if z is to be maximized, then a very large negative price, also called penalty, is assigned to each of these variables. The penalty will be designated by negative big M for a maximization problem and positive big M for a minimization problem where M more than 0. Now, the givens are big M methods is a form of simplex method, but mostly is used for solving the problem of minimization. In spite of it can be used to solve the problem of maximization. The difference between simplex methods and big M methods: if the big M methods are oriented to solve the problem of minimization, we will use artificial variables. We use artificial variables in case of minimization to compensate the negativity of a slack variable. Let me explain this phenomenon. If the constraint or inequality is more or equal, we have to subtract slack variable negative s. As we emphasized, all decision variables must be more or equal 0. In this case, s will be negative, less than 0. So to compensate the negativity of a slack variable, we have to add the artificial variables a. Number 1. Okay. Number 2, if the objective function is to be minimized, then a large positive M should be assigned to each artificial variables. On the contrary, if the objective function is to be maximized, the large negative big M assigned to each of these variables, this which we know as big M. Let's check the steps of applying the Big M methods. Modify the constraints so that the right hand side of each constraint is non-negative. This requires that each constraint with a negative RHS be multiplied by negative 1. Remember that if you multiply an inequality by any negative number, the direction of inequality is reversed. After modification, identify each constraint as more or equal, less or equal, or equal. 3 versions of constraints. So modify the constraints so that this is as condition. You need to modify the constraint so that the RHS right hand side of each constraint, it must be non-negative. Okay. In order to reverse the constraint from type less or equal into type more or equal, we need to multiply this inequality by negative 1. Okay. The form of constraints are 3. Either the constraint more or equal, or the constraints less or equal, or the constraint equal. In our case, if the problem is about maximization, the corresponding constraints must be less or equal. If the problem about minimization, as mentioned before, the corresponding constraint should be more or equal. These are a conditions. Now, the second step, convert each inequality constraint to the standard form. If constraint I is less or equal constraint, we add slack variable si. And if the constraint I is more or equal constraint, we subtract an excess surplus variable ei. Add an artificial variables ai to the constraint identified as more or equal constraint to the end of step 1. Also add the sign restriction ai more or equal 0. So, generally the steps of applying Big M methods is to fix the constraint to the standard form and to artificial transformation. What do we mean by artificial transformation? We mean by artificial transformation adding a stands for artificial variables, or subtract A. Okay, so the first step to convert the constraints or inequalities into standard form by adding or subtracting select variable. Then to transform the constraints into artificial step by adding or subtracting artificial variables. Let M denote a very large positive number. If the LP is a main problem, add for each artificial variables MA to the objective function before equal to 0. If the LP is a max problem, add for each artificial variable negative MA to the objective function before equal to 0. Since each artificial variables will be in the starting basis, all artificial variables must be eliminated from objective row before applying the simplex method. Then solve the transformed problem as simplex by choosing the entering, leaving variables and key element. Remember that M is a very large positive number. M is a very large positive number. This is about to make the objective function zero equation. To make the objective function zero equation. In case of minimization, we will transform the objective function to the equation or zero equation by subtracting the select variables negative s, adding coefficient to select variables equal 0, and by adding artificial variable a with the coefficient equal big M. Remember, the sign of the coefficient of s equal negative 0 and the sign of the coefficient of a equal positive M, actually big positive M. This is the main here. Let's see mathematical formulation of linear programming problem. The procedure of mathematical formulation of LPP consists of the following steps. Step 1. Identify the decision variables of the problem. Step 2. Formulate the objective function to be optimized. maximized or minimized as a linear function of decision variables. Step 3, to formulate the constraints of the problem, such as resources, as linear equations or inequalities. Step 4, add the non-negativity condition. The non-negativity condition. This is known as the procedure of mathematical formulation of linear programming problem. This is the process of mathematical formulation of linear programming problem. The main tool in providing or applying the models or methods of operations research is known as linear programming أو أسلوب البرمجة الخطية، وهو أسلوب رياضي بيهدف إلى تخصيص الموارد النادرة بطريقة أمثل. Linear programming is a mathematical technique aims to optimal allocation of scarce resources. aims يهدف إلى شنو؟ to optimal allocation of scarce resources. optimal allocation of scarce resources اللي هي تخصيص الموارد النادرة بطريقة أمثل. طيب، using two objectives، تخصيص الموارد بطريقة أمثل باستخدام هدفين اللي هو easier to maximize profit أو نقوم بتعظيم الربح or to minimize cost أو نقوم بتدنئة التكاليف. إذن the main aspect of linear programming, the main aspects of linear programming, the main goals of linear programming are two: profit maximization or cost minimization، تعظيم الربح أو تدنئة التكاليف. So each, in order to apply the main tasks of linear programming, so there are three components. These three components are known as the components of linear programming. Actually, here we are talking about the application of linear programming model. هنا المكونات الثلاثة للبرمجة الخطية هي عبارة عن objective function دالة الهدف، constraint القيود، و non-negativity condition اللي هي شرط عدم السلبية. So, in order to design a linear programming model، إذا أردنا تصميم نموذج برمجة خطية، يجب أن يحتوي هذا النموذج على ثلاثة مكونات: دالة الهدف objective function، القيود اللي هي constraints، ثم شرط عدم السلبية أو non-negativity condition. So we will pass these three components separately. separately. The first component is objective function اللي هي دالة الهدف. Let's define what do we mean by objective function. Objective function is a linear equation to maximize profit or to minimize cost. يعني as we mentioned before, linear programming has two goals اللي عندها هدفين: تعظيم الربح أو تدنئة التكاليف. ولذلك دالة الهدف بيتضمن هدفين اللي هو هدف التعظيم وهدف التدنئة. وبالتالي لدينا دالتين للهدف: دالة تعظيم الربح ودالة تدنئة التكاليف. max z equals c1 x1 plus c2 x2 up to cn xn represents the problem of profit maximization. Max stands for maximization, C1 and C2 up to Cn stands for the profit of one unit of product. What that means, C1 is the profit of one unit of product X1, C2 is the profit of one unit of X2, and Cn is the profit of one unit of Xn. So actually, as we mentioned before, objective function is a linear equation. A linear equation معادلة خطية. X1 and X2 and Xn are known as products or decision variable. X1 X2 Xn عبارة عن سلع، وتعرف أيضا بمتغيرات القرار. طيب، in case of minimization objective، إذا كان لدينا of minimization function min z equals c1 x1 plus c2 x2 plus up to cn xn. Min here stands for minimization, while c1 c2 up to cn stands for what here? For the cost of one unit. C1 in case of minimization is the cost of one unit of product X1, C2 is the cost of one unit of product X2, Cn is the cost of one unit of product Xn. Min represents objective function of minimization. Here عندما نكتب ماين قاصدين دالة تدنية التكاليف. الفرق بين دالة التعظيم ودالة التدنية C1 و C2 و Cn في دالة التدنية عبارة عن تكلفة إنتاج الواحدة من السلعة. X1 و X2 و Xn أيضا في هذه الحالة عبارة عن products أو سلع، وأيضا نطلق عليها متغيرات الغرض. هنا قمنا بتصميم دالة الهدف بالنموذجين. Now we design, almost designed as shown, we design two functions, or actually design two objective functions. Objective function of minimization and objective function of maximization. Number 2, constraints, and number 3, non-negativity condition. We said that linear programming problem contains 3 components: objective function, constraints, and non-negativity condition. دالة الهدف، القيود، وشرط عدم السلبية. Constraints are the linear inequalities or equation on the variables of a linear programming. القيود عبارة عن متباينات أقل من أو يساوي أو أكبر من أو يساوي and equations معادلات في نظام البرمجة الخطية. Objective function, as stated before, has 2 forms: easier to maximize profit or to minimize cost. If the objective function is a maximized function, then the constraints will be equal or less. إذا كان دالة الهدف دالة التقسيم فإن القيد دائما يكون أقل من أو يساوي. In case of minimization, the constraints will be more or equal. في حالة الكوست أو التدنئة بيكون القيد أكبر من أو يساوي. Let us take the following example. Subject 2. What that means? The implementation or application of objective function is subject to, is restricted by what? By the satisfaction of the following constraints. For example, the constraints of my maximization is like A11 x1. A11 stands for the cost of 1 unit of x1. A12 x2. A12 is the cost of 1 unit of x2. In the first phase, less or equal P1. P1 is a resources available for phase 1. Let me explain. For example, if the production of a certain product passes 2 phases, phase 1 and phase 2, then the constraints should equal to, if the process of production consists of 3 phases or 4 phases respectively, the constraints should be 3 or 4. Now, x1 and x2 indicates that the decision variable contains 3 products, x1 and x2. b1, b2 up to bn are available resources. These resources may be electricity, time, raw materials, etc. In case of minimization, we are going to change the inequality only from less or equal to more or equal. القيود في دالة التعظيم عادة بتكون أقل من أو يساوي، أما القيود في دالة التدنئة أو المينيمايزيشن بتكون أكبر من أو يساوي. The last component is non-negativity condition. x1, x2 more or equal 0. This condition shows that easier to produce or not to produce x1 or x2. To produce means more than 0, not to produce equal 0. Therefore, this condition easier to be more than 0 indicates the process of production is going or equal 0 or equal 0. Three components: objective function دالة الهدف, constraints القيود, and non-negativity condition اللي هي شرط عدم السلبية. The second version of linear programming problem is how to formulate an objective function of minimization. Let us follow the following example of minimization. A nutritionist wishes her client سؤال بتاع التغذية wish her client to have a daily 30 units of vitamin A, 20 units of vitamin D, and 24 units of vitamin A. What that means? That means nutritionist has a total unit of vitamin A equal 30. Total units of vitamin D equal 20 milligram, and D equals to 24 units. This is the stock available for nutritionists. Now, so let's see the combination y1 and combination y2. The combination y1 should consist of 2 units of vitamin A, 5 units of vitamin D, and 2 units of vitamin A, E. The total cost of combination Y1 equal $80. From the next hand, combination Y2 contains 6 units of vitamin A, 1 unit of vitamin D, and 3 units of vitamin E. The stock is 30 units of vitamin A, 20 units of vitamin D, and 24 units of vitamin E. The cost of combination Y2 equal 160. Please follow the diagram to understand the division and classification or breakdown of the problem. So here we have statement which determine the nature of linear programming problem. The statements talks about cost once, and therefore we have to formulate a problem of minimization. The objective function have to express problem of minimization. Objective function consists of two costs per units of combination, $80 for Y1 and $160 for Y2. Nutritionist faces 3 vitamins respectively. We have to design 3 constraints. One constraint for vitamin A, other constraint for vitamin D, and the third constraint for vitamin E. The last part of the components of LP is non-negativity condition Y1, Y2 more or equal 0. Refer notice. Refer to the previous problem of minimization. Objective function is a minimization function. Therefore, it consists of the cost of 1 unit of combination Y1 or Y2. Constraints are formulated as an expression of each vitamin. Respectively, the objective function is min z equal 80 y1 plus 160 y2. $80 and $160 are the cost of 1 unit of each combination respectively. This is known as objective function for minimization. This objective function should minimize the cost of production of combination 1 and combination 2. This objective should be applicable if and only if the following three constraints are satisfied. Two y1 plus 6y2 more or equal 30. This constraint expresses of vitamin A. So vitamin A costs 2 in the first combination and equal 6 in the next combination. So 2 units is the cost of y1 and 6 units is the cost of y2. Available quantity of vitamin A is 30 m. The second constraint stands for vitamin D. The cost of y1 of vitamin D 5 units. The cost of vitamin D for y2 equal 1. The total available quantity is 20 ml. The last constraint expresses the cost of vitamin E, where in this combination the cost of 1 unit of y1 equal 2 units and for y2 equal 3. The total available quantity of vitamin E for nutritionists is 24 units. The last component is non-negativity condition, where y1, y2 either equal 1 or greater than 1, greater than 0 or equal 0. This is the last how to formulate a LP program, linear programming problem, which include objective function, constraints, and non-negativity condition. Steps of the graphical methods, or steps of application of graphical methods, or how to apply the graphical methods. 1. The problem is expressed in the form of a mathematical model. 2. Consider each inequality constraint as equation, or convert constraint into equation. Plot each equation on the graph, as each equation will geometrically represent a straight line. Shade the visible region and identify the visible solution. Every point
on the line will satisfy the equation of line. If the inequality constraint corresponding to that line is less or equal, then the region below the line lying in the first quadrant due to non-negativity of variables is shaded. For the inequality constraints with more or equal sign, the region above the line in the first quadrant is shaded. Understand? The point lying in common region will satisfy the constraint simultaneously. Thus, the common region obtained is called visible region. This region is the region of visible solution. The corner points of this region are identified. So, in the next slides, we can apply practically these 4 steps. You can apply these 4 steps practically using various examples. Okay. Decision making environment. To make a decision is depending upon environment. The form of decision is controlled by the environment in which the decision is making. Decision analysis is aimed to determine optimum strategies, or decision analysis is aimed to make a best decision or to determine an optimal strategy where a decision maker is faced with various alternatives. In this manner, we classify 4 forms of environments. These environments impacts on the design of a decisions. 4 forms of environment under which the decisions are taken. Decision and certainty. Certainty means there is no doubt related to outcomes. Everything is given: information, data, fact. So, no doubt about the related outcomes which resulting from the decision under certainty. Suitable examples are decisions that cause the deterministic problems: linear programming, transportation model, assignment model, sequences model, etc. the most complicated decisions which are taken under uncertainty. This refers to situation where more than one outcome can result from any single outcome. So, we will give special attention to this environment. The environment under uncertainty is called uncertainty. Uncertainty, it is an environment. Certainty, it is environment. Risk, it is environment. Conflict, it is environment. Decision under risk refers to decisions wherein the decision maker chooses from among several possible outcomes. We will neglect this form of decision. The last decision under conflict. Neither states of nature are completely known nor are completely uncertain. We are not going in depth to explain this form of environment. Once the decision under certainty is known, or we almost tested this form of decision by explaining the linear programming methods. Then we will focus on the decisions under uncertainty. The decisions under uncertainty. We already made a decision under certainty by explaining or by passing simplex methods, graphical methods, transportation methods, assignment method, etc., and dualistic methods. Generally, we will focus on the decision under uncertainty. Okay, as we promised, we will center our approach on the decision under uncertainty. There are 5 approaches of decision under uncertainty. Maximax or Minimax criterion, Hewitt's criterion, Laplace criterion, Minimax regret criterion, Maximax criterion, Maximine criterion. So let's introduce with criterion of pessimism. التشاؤم. Minimax or Maximin. Maximin is a conservative approach to assume worst possible outcomes. This approach involves 2 steps. First, we need to find the minimum payoff for each alternative. That means we need to construct a table of payoff. First step, to find the minimum payoff for each alternative. Step 2, to choose the maximum of minimum value. First, determine the minimum, then to choose a maximum among these minimums. Minimax, from other hand, involve two steps, opposite of that manner. To determine the maximum payoff, then to choose the minimum of that maximums, of those maximums. Minimax, again, to find the minimum payoff for each alternative. Okay, so that means all our payoffs are minimum. Then among these minimums, there is more minimum, max minimum. The max minimum, the maximum of minimum, is max min. Otherwise, in option of minimax, we need to determine the maximum payoff. Inside this table of maximums, we will choose the minimum of those maximums, this which is known max min and mini max. Criterion of optimism and Laplace criterion, minimin or maximax. Again, the criterion based on extreme optimism, where decision maker should not miss the opportunity to gain the greatest possible payoff. The steps of conducting maximax: determine maximum possible payoff, then select an alternative which corresponds to maximum of above maximum payoff. Easy. Now we design table which consists of various maximums. For example, 2, 3, 4, 5, 6, 7, 8, 9. From 1 up to 9 or up to 10, there are 10 maximums. Then the maximum of these maximums is 10. Then the alternative of 10 should be chosen, because the maximum of maximum. Minimin, on the contrary, table consists of various minimums starting from 1 up to 10. The minimum among these 10 alternative is 1. Say, for example, 1 belongs to alternative A, then A should be chosen because it got the minimum of the minimum. This which we call the criterion of optimism. You have to distinguish between the criterion of pessimism and criterion of optimism. Max-min or min-max is a criterion of pessimism. Mini-min or maxi-max are the criterion of optimism. التشاؤم والتفاؤل. Okay. Laplace criterion. This criterion assumes that all states of nature will occur with equal probability. Probability is given by 1 over number of states of nature or event. If the events are 3, then the probability equal 1 over 3. If the events are 4, then the probability equal 1 over 4, and involves following steps. First step, assign equal probabilities to each payoff of a strategy. Then determine the expected payoff value of each alternative and select alternative of some of maximum payoff or minimum cost. Wonderful. Okay. Laplace criterion. First step is to determine the probability. Equal probability. Probability is given by 1 over the number of states of nature. We don't know how the states of nature, maybe 9, 10, whatever. And then after that we are going to insert the following steps. Assign equal probability to each payoff, then determine the expected payoff value for each alternative, and select alternative with the maximum payoff or minimum cost. Don't worry, we will apply practically these approaches or criterions. Okay, here is criterion or criterion of realism. This criterion suggests that a rational decision maker should neither be completely optimistic nor pessimistic. اتخذ القرار لا متفائل لا متشائم. And therefore must display a mixture of both optimistic and pessimistic, which discover the idea of a coefficient of optimism, alpha, which lies between 0 and 1. Thus, if alpha is the coefficient of optimism, then 1 negative alpha represents the coefficient of pessimism. Steps. Decide the coefficient of optimism alpha and of pessimism 1 negative alpha. Then determine the maximum and the minimum payoff. Find H equal alpha times the maximum for each alternative plus 1 negative alpha times the minimum of each alternative. Select the alternative with the highest value of H. coefficient معامل طبعا. Decide the coefficient of optimism alpha and of pessimism alpha minus 1 minus alpha. Then determine the maximum and the minimum payoff. The last column. H equal alpha times maximum for each alternative plus 1 negative alpha times the minimum of each alternative. Select the alternative with the highest value of H. Criterion of regret, nadam or minimax regret. In this case, decision maker feels regret after adopting a wrong alternative, resulting in an opportunity loss of payoff. Feelings of regret, شعور بالندم. Steps: develop an opportunity loss or regret matrix. The best payoff to each state of nature. Of course, maximum for profit and minimum for cost. Then determine the maximum regret. Inside or among these maximums or maximum of regrets, choose the alternative with the minimum regret. There are various levels of maximum regret. Inside this, among these levels of maximum regret, choose the minimum regret of those maximum regrets. Steps of application assembly methods. Step 1. Convert constraints to standard form and make objective function zero equation. We clarified before that by adding or subtracting slack variable, we converted the constraints to equations or standard form. Number 2, design the primal table by substituting the coefficients of variables. This primal table or essential table، الخطوة الأولى هي تحويل القيود إلى معادلات بإضافة S في حالة إن القيد يكون أقل من أو يساوي، أو بطرح S في حالة القيد يكون أكبر من أو يساوي. القيد أقل من أو يساوي معناها نتحدث عن مشكلة بتاع التعظيم، أكبر من أو يساوي معناها نتحدث عن مشكلة تجميع التكاليف. طيب، ثم تحويل دالة الهدف إلى معادلة صفرية. Step 2 اللي هو to design the primal table. The primal table consists of the first row of the basic variables. الصف الأول في هذا الجدول the upper row، جدول الصف الأعلى represents the basic variables، المتغيرات الأساسية. The first column to the right, to the left, represents non-basic variable. Right. Our target to move the decision variable from the non-basic row to the basic column of variables. Right. The contents of the cells of the table consist of the coefficients of variables. For example, the first constraint is 2x1 plus 3x2 plus s1 equal 40. That means 2 is the coefficient of x1, 3 is the coefficient of x2, and 1 is the coefficient of s1, and the solution equal 40. Later on it will be easy to understand. Step 4, select entering and exiting leaving variables. نحدد المتغير الداخل والمتغير الخارج. Find the pivot element اللي هو العنصر الأساسي، the main element. Determine the main equation، pivot equation، معادلة المحور، عنصر المحور. Apply the process of leaving and entering values. Iterate the solution up to disappearance of the negative values in objective function or zeta function. Prove the solution. طيب، where the end of the solution? When we capture the optimal solution. متى نصل إلى الحل الأمثل؟ حل مشاكل السمبلكس يقوم على التحديث iteration إلى أن نصل إلى حالة اختفاء القيم السالبة في دالة الهدف. عندما تختفي القيمة السالبة في دالة الهدف نكون وصلنا إلى الحل الأمثل. We reach the solution, the optimal solution, when the negative value in the objective function are disappear. عندما تختفي القيم السالبة في دالة الهدف، حينها نكون وصلنا إلى الحل الأمثل. في حالة التنمية عندما تختفي القيم الموجبة. In case minimization, we reach the optimal solution in case of minimization when the positive value are disappear. The difference between two methods. Now let's see how to apply these steps practically. Slack variable, as mentioned, represents the unused resources ويعبر عن الموارد أو المواد التي لم يتم استغلالها. When the constraint is less or equal, slack variable should be added, otherwise should be subtracted. For example, given the following linear programming problem where max z equal 4x1 plus 10x2 subject to 2x1 plus x2 less than 50, 2x1 plus 5x2 less than 100, 2x1 plus 3x2 less than or equal 90, x1 x2 more or equal 0. Right. Now الو فايز، كيفك؟ اخبارك؟ Now the first step to convert inequalities constraint to standard form. Once inequality is less or equal, then we are going to add s1. 2x1 plus x2 plus s1 equal 50, 2x1 plus 5x2 plus s2 equal 100. The last constraint 2x1 plus 3x2 plus s3 equal 90. Notice that the slack variable for constraint number 1 is s1. The slack variable for constraint number 2 is s2. The slack variable for constraint number 3 is s3. That's why. So s1 represents first constraint, s2 represents second constraint, s3 is for the third constraint. يا فايز ما بسمعك يا اخوان.
من وين هو؟
السودان بكم. Okay. So here we converted the objective function to zero equation. Z minus 4x1 minus 10x2 equal 0. It was Z equal 4x1 plus 10x2. So we pushed the 4x1 and 10x2 to the left side and we got z minus 4x1 minus 10x2 equals 0. This is a zero equation. Now the contents of the primal table. Check the first row. The upper row consists of x1, x2, s1, s2, s3 and solution. The values inside these cells represent the coefficients of variables. Now, if we return back to the standard form, 2, it is a coefficient of x1 in the first constraint, or in the first standard form or equation. 1 is the coefficient of x2. The next one is the coefficient of s1. In the first constraint, there is no s2, respectively there is no s3, then their coefficients is 0, 0. The solution is the resources b in case of the first constraint. طيب. S1 يعبر عن القيد الأول. إذا رجعنا إلى الستاندرد فورم، القيد الأول هو عبارة عن 2x1 plus x2 plus s1 equal 50. إذن 2 هي معامل x1 و x2 المعامل بتاعها 1 و s1 المعامل بتاعها 1، وليس لدينا s2 و s3، لذلك المعاملات ل s1 و ل s3 هي 0 0. 50 هي عبارة عن الموارد. S2 تعبر عن القيد الثاني. في القيد الثاني معامل x1 2، معامل x2 5، ليس لدينا s1 في القيد الثاني ولذلك المعادل 0. هنالك s2 في القيد الأول المعامل بتاعها 1، وليس لدينا s3 في القيد الثاني ولذلك المعامل 0. السوليوشن هو عبارة عن 100 وهي الموارد المتاحة للقيد الثاني. القيد الثالث عبرنا عنه بالمعادلة 2x1 plus 3x2 plus s3 equal 90. اثنين هو معامل x1 في القيد الثالث، 3 هي معامل x2. لا يوجد لدينا في القيد الثالث s1 و s2 ولذلك معاملاتها هي 0 0. s3 في القيد الثالث هو معاملها 1. الموارد المتاحة للقيد الثالث هي 90. Now the first check the second row which stands for S1. Where is 2 is coefficient of x1, 1 is the coefficient of x2, s1 is the coefficient of s1. In the first constraint we have no s2 and f3, then their coefficients are 0 0. The solution is 50. Move to the second constraint. S2 represents the second constraint where the coefficient of x1 is 2, the coefficient of x2 is 5, no s1 equals 0, the coefficient s2 equal 1, s3 equal 0, the solution is 100. S3 represents the third constraint where 2 is the coefficient of x1, 3 is the coefficient of x2, 0 0 and 1 the coefficient of s3. The available resources equal 90. Z the first is negative 4 and negative 10. There is no S2, S1, S3 solution, therefore equal 0. Therefore equal 0. Refer to the primal table. Please copy the table and follow the steps. رجاء أنقل الجدول لكي نسهل عليكم عملية فهم الحل. Please copy the table and follow the steps to simplify the process of solution. Step 4. We need to determine the entering value. المفروض ندخل هو مش we need to determine the entering variable, not value. The definition of entering variable is that variable which faces the biggest negative value in the row of Z. ما هو المتغير الداخلي؟ entering variable. entering variable متغير الداخل هو المتغير الذي يناظر أكبر قيمة سالبة في دالة الهدف. Return back to the primal table. We found that the biggest negative value in the last row or the row of Z, we found the biggest negative value is negative 10. And the variable which faces this negative 10 is x2. Notice please, x2 is placed in the upper row. This x2 faces negative 10 in the lower row. Then we call x2 is entering variable, متغير الداخل الذي يناظر أكبر قيمة في دالة الهدف. المتغير الداخل هو نجده في الصف الأول أو الصف الأعلى non-basic variable، في صف non-basic variables. هو متغير الداخل أو x2 should be converted transform from non-basic to basic variable. So it will substitute leaving variable. We mentioned before that the first left column consists of basic variable. The first upper row consists of non-basic variable. We need to convert x1, x2 from non-basic to basic variable. So, to replace easier S1 or S2 or S3. So now x1 should replace easier S1 or S2 or S3 to replace the leaving variable اللي هو المتغير الخارجي. Now how to determine the leaving variable? Let's use the calculation. Check the right column of solution and check the column under x2. We are going to divide the column of solution over the column under x2, except the negative and zero values. Except the negative and zero values. Now, we found 50 over 2, 100 over 5, and 90 over 3, respectively equal 50, 20, and 30. The least value is 20. We found 20 by division 100 over 5. 100 over 5 is calculated. The result of calculation in the row of S2. Then S2 is said to be leaving variable, said to be leaving متغير خارجي. كيف نحدد المتغير الخارجي؟ ننظر إلى عمود الحل، وهو العمود الأخير على اليد اليمين. نقوم بقسمة كل القيم الموجودة في هذا العمود على ما يناظرها من القيم الموجودة تحت أو في عمود المتغير الداخلي، وهو عمود x2. إذن سوف نقوم بقسمة 50 على 1، 100 على 50 على 5، و90 على 3. أقل قيمة من حاصل هذه القسمة هي 20، وهي عملية حدثت في صف S2 أو الصف الثالث، ولذلك نعتبر S2 متغير خارج ليحل محله X2. ثم then we are going to determine the pivot element أو العنصر المحوري. The pivot element is the intersection cell خلية or value between the entering and leaving variable. هي القيمة التي تقع في نقطة التقاطع بين المتغير الداخل والمتغير الخارج، إذن بين x2 و s2، وهي تساوي 5 إذا عدنا إلى البرايمال table. Pivot element is intersection value or cell between the entering and leaving variable, then equal 5. Step number 7 is to find the pivot equation. The pivot equation is exiting row or leaving row over pivot element. Then leaving row over pivot equation. Exiting row or leaving row is the row of S2. 2, 5, 1, 0, 100 over 5 pivot element. The result is 0.4, 1, 0.2, 00, 20. This is known as pivot equation, or the values of x2 in the next table, replacing S2 يعني S2 will be kicked out. Instead of S2 we will replace X2. بدلا عن S2 هتكون عندنا X2. Now X2 is moved from non-basic variable to basic variable. We pushed, transformed, converted X2 from non-basic to basic variable. S2 gone out of our optimal solution. Okay, the entering of X2 as basic variable will lead to change in S1, S3 and Z, resulting from the entering of X2 as basic variable. How S1 will change? Check the following table to determine the new S1. Why new S1? The new S1 is the resulting from the entering of X2 as basic variable. The first row copied the values of S1 as given in the primal table. Let's check the pivot element of S1. The pivot element of S1 equal 1. Intersection point or intersection between S1 and X2 as entering value. العنصر المحوري ل S1 هو ذلك العنصر الذي يتقاطع مع عمود X2, which is determined as entering variable. Now, this pivot element should be multiplied by pivot equation, which also is determined before. The results are 0.4, 0.2, 0020. This is the result of multiplication of pivot element of S1 times pivot equation, and we subtract 0.4 from 2, 1 from 1, 0.2 from 1, etc. New S1 is 1.6, not 1.8, and 110, 1.8, 0, 0, 50, negative 20 is 30. This is a new, how to find the new S1. How to find the new S1. The same scenario, how to check the change in S3 resulting from the entering of X2 as basic variable. We are going to copy S3 as given in the primal table. The second operation represents by the second row, pivot element of S3 multiplied by pivot element which is given, this is the result of multiplication. 1.2 3 0.6 00 60, and new S2 is 2 negative 1.2 is 0.8, 3 minus 3 is 0, 0 negative 0.6 is negative 0.6, 0 minus 0 0, 1 minus 0 1, 90 minus 60 is 30. This is a new S3, the new S3, and this is the impacts of S3 by the entering of x2 as basic variable. As you see, we just repeat the same steps in determining the effects of new basic variable. Last step also we will repeat the same instructions in determining the new z as a result of the entering new basic variable x2. Copy z as given in the primal table, negative 4, negative 10, remain 0. Pivot element of z multiplied by pivot equation. The harvest is negative 4, negative 10, negative 2, 00, 100. So we will get the table below. As you see, there is no all the values are positive. There is no negative values in Z row, where S1 is 30, X2 is 20, S3 is 30, Z is 200. There is no X1, that means X1 equals 0. There is no S2, that means S2 equals 0. So this table shows that S1 equal S3 equal 30, S2 equal 0, X1 equal 0, X2 equal 20, and Z equal 200. Now prisoner's dilemma. A prisoner's dilemma is a situation where individual decision makers always have incentive to choose in a way that creates a less than optimal outcome for individual as a group. If it occurs in many aspects of economics.
Prisoner's dilemma is a paradox in decision analysis, in which two individuals acting in their own self-interest don't produce the optimal outcome. The prisoner's dilemma was developed in 1950 by Rand Corporation mathematician Merrill Flood and Melvin Treasure during the Cold War, but later given its name by the theorist Alvin Toffler. Today, the prisoner's dilemma is a paradigmatic example of how strategic thinking between individuals can lead to suboptimal for both players. Key points of prisoner's dilemma. A prisoner's dilemma is a situation where individual decision makers always have an incentive to choose in a way that creates a less than optimal outcome for the individuals as a group. The prisoner's dilemmas occur in many aspects of the economy. In the classic prisoner's dilemma, individuals receive the greatest payoffs if they betray the group rather than cooperate. If games are repeated, it is possible for each player to devise a strategy that rewards cooperation. People have developed many methods of overcoming prisoners' dilemmas to choose better collective results despite apparently unfavorable individual incentives. Understanding the prisoner's dilemma. A typical prisoner's dilemma is set up in which a way that both parties choose to protect themselves at the expense of the other participants. As a result, both participants find themselves in a worse state than if they had cooperated with each other in the decision-making process. The classical example: two prisoners are accused of a crime. Each of them has two choices: either to confess or to deny in response to the guarantee given by the police authorities. If both deny about the crime, the both get jailed for 2 years each. If both confess that you both did the crime, you get 1 year, whereas the other get 10 years jail. If you deny and partner confesses, you get 10 years and partner get 1 year. If both of you confess, then both of you get 3 years each.